Okay. Yeah. Hi. Hi, everyone. So let's start the session. Before we go over the materials, is there any question about either the assignment, the materials? No? Not any question? Okay. So, what?
Are there any further instructions? Or it's just that?
What do you mean?
Any further instructions for the assignment one solutions?
For the assignment one, I can say that assignment one is a good estimate of what type of questions you will have in your midterm exam. So as I said, in the midterm exam, I will not ask for any proofs, but it will be usage of the algorithms for different machine learning tasks with some toy examples, either 2D, 3D. We might have 3D, and 3D points, I mean. I think it's obvious what I mean. And I will not make it challenging, and I think it will be straightforward. And the exam will be open book because I don't want you to memorize anything, just understand the algorithms. Okay. And yeah, and the exam will be in person. And yeah, this is, and hey, I think we have some inverses of matrices. So for that, either you can use your calculator or online tools for inverse of matrix. It doesn't matter. Yeah, something like that. And we will not extend the deadline because I need to post a solution afterwards for you to know the solution questions and solutions for the exam to study for. Yeah, that's it. And soon I will make an announcement for forming the teams. It's time to form the teams, and also write your proposals, just 1 or 2 paragraphs. There is no grading for proposals, for us just to verify whether it's a good project or not. And yeah, we'll probably have a second assignment afterwards, and that's it. So 2 assignments, 1 midterm, 1 project, and 1 presentation. That's okay. And if there is any question about the assignment or anything about the material, please feel free to ask me and or the TA. Okay. So tree and random forest, we started that in the previous session. Tree. So what did we say? We said tree is used for either classification or regression. It's used a lot in various fields of science. It has been used in even optimization. For example, for non-convex optimization, branch and bound method in optimization uses tree. And also in machine learning, we have tree for classification. What? I think I have mentioned it in one of the slides, for introductory slide of the course. Yeah, okay. So as I said, tree is easy to implement and it is intuitive. So it explains how it is working. So it can be considered as explainable AI. So it explains, it's not mysterious why it is working. And also it is common to use in biostatistics and health sciences. Okay. So we have a data set. We said that the data set is d-dimensional, and every data point is a d-dimensional vector, and the label is a scalar. If it is a classification problem, the label will be discrete, but if it is a regression problem, the label would be continuous. And let xij denote the jth dimension or feature of xi. Then what does a tree do? A tree partitions the space into regions. It splits over one of the features at every split. So at every split, we take one of the features and we split it over it. So for example, in this example, you see a tree for here at the top, we say, so xi1, it means that we are considering the first dimension, which is this here. And if it is less than S1, we go left. If it is greater than S1, we go right. So we partition in this. And then if here, if it is xi2, now that second dimension, if it is less than S2, we go left. If it is greater than S2, we go right. So we have region 1 and 2 as drawn here in this figure. And also the rest of the branches, we already explained them before. So as you see, 3 partitions the space, and this is a binary tree because at every split we split into 2 parts. Okay, and we said splitting the initial region is the whole space, and then a binary tree splits the region into 2 disjointed subregions whose union is the parent region. So they are disjointed, but their union becomes the parent region. As we mentioned in these equations, so R1 and R2 means the 2 children regions from the parent region. The parent region here is denoted by R. Okay, there are several questions. First, over which feature J do we split? Okay, which feature do we split at that depth of the tree? For example, what is the value of the threshold? What threshold do we use for the split? And what constant value should we assign to every region? Because we want to estimate every region by some label. So we said, okay, we define a local cost function as mentioned in equation 5. What does it do? It says I have the labels yi and x4. I'm summing over the regions, the points in the regions. So here, this is the sum over the points in region 1, child 1, and this is the sum over the region over the points in child 2 or region 2. Yi are the scalar labels, and C1 bar and C bar 2 there are the estimated labels of the regions that we assign to the regions. Okay, and why do I put bar? Because I'm putting bar because I'm taking average. Usually I take the average of the labels. You need to do some kind of summary statistics of the labels of the region. It can be average, median, whatever you want. But for example, for median, I think you can use various things such as average, L2 norm, median. And we have various ways to do the summary statistics, but average is the most common one. So average of the labels for the points in the region 1 and average for the labels, average of the labels for the points in region 2. They give us C bar 1 and C bar 2. So what does this do? What does equation 5 do? It says that I find J and S where this cost function is minimized. And as I told you before, it's a discrete optimization because J goes from 1 to J goes from 1 to D. Yes, it's the feature. And S, how many values do we have for S? We said, so we have x1 to xn, for example, in the data set, and the Jth feature, we can see they have some values. If we sort these values, then they give us at most n or n plus 1 regions, possible values for the threshold. So we can say that we'll have a nested loop for this optimization. One loop is over the J for J from 1 to D, and one is over the S for S from values across all of the data points, and it is at most n. So it is in the order of d times n, a complexity, big O notation, right? D over n, and then in the nested loop, we see which one gives us which combination of J and S give us the least amount of this equation 5, and that's the answer. Okay, so now we have answered which feature should we split over, and also what is the value of the threshold. Okay, so we already have answered these 2 questions. And also we also answered the third question, which is what constant value should we assign to every region, and that's equations 6 and 7. Okay, so question 1 and 2 is are answered by equation 5, and question 3 is answered by equations 6 and 7. Right? Everything is clear? Okay. Yes, 3 is easy. I agree. But we will finish it and we'll go to more interesting parts. So if the depth of the tree is small, then the number of children regions is small. So we can have underfitting and overfitting in tree, right? If the depth is too small, we don't grow the tree too much, then the regions will be big and it's not fine-tuned enough. It means that it's underfitting. If we grow it too much, in the worst case, what happens? Every region will have 1 point, because a region without any point, we can't estimate anything for it, right? Every region will only have 1 point. So every point will fall in one region. It's the most worst case scenario, right? So that's complete overfitting. Then underfitting is not good, overfitting is not good. We need a middle case scenario. So what do we do? So we have already explained that. Yes, therefore, the number of children nodes in a tree, denoted by T, is a good measure of overfitting and complexity, right? Let the number of children in the tree be denoted by cardinality of T. So what do I mean? So I have this tree. How many children does this tree have? 3, right? Or terminal nodes. So cardinality of T here for this tree is 3, right? Okay, so this discrete number is a good measure of overfitting for the tree. Now, how large should a tree be not to overfit? So solution 1, we have several solutions. Solution 1, keep splitting the tree until the validation error or generalization error, right, starts going up while the training error is going down. Exactly what we do in early stopping in deep learning. So we keep track of training error and generalization error or validation error, maybe with some oscillation, but ignoring the oscillation, the pattern usually for the training error goes down, but the validation error goes down up to some point and then goes up. The pattern, I mean, we might have some oscillation, right? Then what happens? So we can, by keeping track of validation error and true error, we can find out where we should stop growing the tree. Exactly what we do in early stopping. And why can we do that? This technique can be used in any algorithm which is iterative, because the model complexity axis in this plot can be seen as the iteration index, because the more we train, the more complex the model becomes, right? Therefore, for every iterative algorithm, such as deep learning, such as tree and these things, we can keep track of validation error and training error and know where to stop. So that's one thing. And by the way, this explains why the validation error goes up. For more information, see the lecture on the overfitting, right? Regularization and overfitting. We already talked about that. So another solution, second solution, is that let's define a global error. And what is this global error? It is this. So equation 8, we are summing over the terminal nodes or the children nodes, and NM, what does it say? Is the number of data points in the child region Rm. Okay, every child region has some number of has some points, right? The cardinality of the points in that region we denote it by NM, and as I said, summation is over the children nodes. Okay, and QM here is the average error of the child region Rm, defined as this. What is this? See equation 9, QM. What is this? I'm defining it as 1 over NM, summation over the points in the region Rm, and this is the square error of yi and c bar m. What is c bar m? Do you remember? This is the average estimated label for the region Rm. I told you already. C bar m is the average of labels in the region Rm, which is estimated label for that region. And this basically is saying what is the average error or the mean squared error. Why? Because this is mean and this is a squared and this is error. This is the whole thing is mean This is a squared and this is error. So this is a mean squared error of the labels in the region Rm, the child Rm, right? And what do we do? We sum over all of the children. So this gives us a kind of a global error of the tree, right? So we can do that and we can consider this. And then what do? We can calculate the global error of the tree after every split. Every split that we do, we have on the tree, we calculate this equation 8, the global error. And then if there is not sufficient decrease in the global error, then we stop. An example is this figure. So the global error, assume the y-axis here is the global error, equation 8. So it is going down. Yes, it is going down, but at some point, you might not have enough decrease, such as this, not enough decrease. Then we stop. That's another. So I'm repeating what I said here, but is it a good solution or not? With this example, I show you that it's not a good solution. Why? Before seeing that, can you tell me why it is not a good solution? Is it wise to calculate the global error and stop whenever we don't have enough decrease in the global error? By this, what are we doing? We are only looking at in front of us, right? We're only looking at in front of us. Maybe there is a well in front of me, so I stop walking. But what if the reward is after the wall? The well, right? So there is a well, I see the well, I say, okay, I stop walking, I don't continue. But if you jump, if you continue, maybe there is a treasure after the well, right? So it's only taking into account the short-term reward. What if there is a long-term reward? So as you see here in this analysis, it's a bit related to reinforcement learning. So what do we say? Here, the solution is not good because what if the global error in the next split suddenly decreases drastically? Do you agree? So for example, it was like this, but maybe in the next split, suddenly it becomes like this. Why do you stop here? Yeah, maybe in the next, an example is this. Consider these two classes. This split says that it's not good, right? So stop, because these are confused with each other. These are confused with each other. However, this becomes good in the next one, in the next split. This, the next split, separates these two completely. And this needed the help of the previous split. Needed the help of them, right? Therefore, this is not a wise decision. We need to take into account long-term rewards. Okay, solution 3. Another solution is to use regularization. We see a lot of regularization in machine learning. So what do? We grow the tree by the local error optimization for every split. We already talked about this, right? This is the nested loop. We already talked about it. So using this, we grow the tree. Using this, we find out at every split which J I should use, which dimension I should split over, and which threshold, S, right? Then, so you grow as much as you want, and then prune it. And then prune it. So prune it by the regularized global error. So this global error we already talked about, right? But we are making it regularized. So we are adding a regularization term, alpha, the number times the number of children, terminal nodes. Okay, and alpha should be greater than 0. Why? Because we want to minimize that. And if alpha is negative, then it means that we are maximizing the number of children. However, we want to minimize the number of children. Why? What's the reason or rationale for this regularization term? It's because we don't want to have too many children. Otherwise, we'll overfit. This is the penalty on the overfitting. It's a penalty on the number of children. Therefore, it's a penalty on the overfitting, right? Okay. Now, we already talked about QM also in the previous slides. So pruning that I talked about is the opposite of splitting regions. It's the opposite. So splitting splits a parent region into 2 subregions. Pruning merges them, merges 2 children regions into 1 parent region. Okay, it is collapsing or merging child regions into the parent region. So the parent region becomes a new child again. What do I mean? An example is this. I have this. If I prune this, what happens? I merge them. So I will have this. This new, so I'm getting rid of these 2 things. So this becomes a new child. The parent itself becomes a new child. Okay. For pruning, we merge the child tree, merge its children. Which one? Now I'm telling you how to prune. Which has the smallest regularized global error. This is the regularized global error. Do you agree? We already talked about it. But which among the, so for example, here we have 3 children. This, right? Let me have a larger tree because I think this makes more sense. Like this. How many in this tree, how many options do I have for pruning? In this iteration, either this or this, right? In this iteration. After one prune, again, I can prune further. So in this iteration, I have these 2. Which one do I prune? Which one do I get rid of? The one which minimum. What?
Which has the minimum.
Yes, exactly. The one which has the minimum regularized global error. But why? What's the justification for this? Why do I prune the children which minimizes? Okay. This global error for a tree, consider a tree. I want this global error to be minimized. Why? This means this is the mean squared error of the labels, of the estimation of the labels, right? And this is the amount of overfitting. I want both of them to be reduced. The mean squared error of the estimation and the overfitting. Both of them should be reduced. So a tree is good. Among the trees, the tree is good, which has the least amount of this global error. But why do I consider the children with minimum value of this to be pruned? Because those children will have the least amount of the role in decreasing this cost. Did you get it? Think about what I'm saying. I want this to be minimized in the tree, decreased. This set of children have decreased this amount with some value. These also decrease them, okay? If I get rid of this improves, goes up. If I get rid of the left ones, the equation 1 also goes up. But I want equation 11 to go up the least amount, right? So I should know which one increases this equation 11 the least. Therefore, I need to minimize. I know it needs a bit of thinking. Again, let me repeat. So,
but if we remove the one which had the larger value, wouldn't the global leveling?
It will be worse. I'll tell you why. For example, so I have two options. Let me say in this way. One option becomes like this. I have two options for pruning. One option, I prune the left one, right? Another option, I prune the right one. Do you agree? So far agree? Two other. So let me call it one, let me call it two. In this one, I prune one. In this one, I prune two. Okay? Now assume equation 11, I call this value V. Okay, I call it V, the value of this class. Assume the V here is 15. Okay, if I prune one, the V, for example, becomes 13. Sorry, it goes up. It becomes 17. Why does it go up? Yeah, because the more fine-tuned we become, the global cost on the training data goes down. Of course, training error always goes down. But our worry is that when should we stop, or how much should we prune so that validation error doesn't go up? You get it? I mean, always by growing your tree, this equation 11 goes down for training data. Okay, therefore, when you prune, this training global error goes up. Okay, by some value. This is an example. So assume the global error.
But if the global error was 15 before.
Yeah, but
if because of prune 2, it's like
yeah, I'm telling you. For example, this becomes 20. Okay. Okay.
If we remove the larger value, wouldn't the average go down?
No, that's it. Let me explain until the end, and I think it will be obvious. So assume this is the global error before pruning is 15. After prune 1 becomes 17. After prune 2 becomes 20. What does it mean? V for these three, or sorry, V for prune for children of children 1, I mean these two, is what? 17 minus 15, 2. Right? I think it's obvious now to you. V, now in this one, V for children 2, I mean these two, is what? 20 minus 15, 5. This is exactly the value of equation 11 for these two children. So which one is minimized? This one. Therefore, prune 1 is better. Why? Because it has the least amount of role in decrease of global error. Because if I have these children, they reduce the global error by 5. But if I have these children, they reduce the global error only by 2. Is it obvious now? Did you get it? No? Okay.
No, I was thinking on a way, like, if we are averaging it, like the global error is an average.
Yes.
So if we remove the largest term, the average should go down in general, like without this concept.
The average, if we prune, the error goes up. If we prune, if we grow, the error goes down.
If we prune, the error goes down.
No, if we prune, the error goes up, like this. V was 15. After pruning, it became 17. Why? Because if we grow, the error goes down, and pruning is the opposite of growing. So if we prune, the global error should go up. But how much does it go up? I want it to go up the least amount. Therefore, I minimize. Agree? Okay. I agree. It needs a bit of thinking. Okay. Now, question. Why do we grow the tree until long and then prune? Are we sick? Why do we do that? Why do we get ourselves tired, grow the tree until the end and then prune? We just go until where we wanted to prune. Exactly, because of long-term reward that we talked about. Because you don't know what you will see several steps ahead. So go until the end, see everything, and then come back. Explore the world, and then come back. Okay? That's the reason. Okay. Now, algorithm of regression tree in summary. As I said, tree can be used either for regression or classification, right? Now, algorithm of regression tree in summary. Grow the tree iteratively or recursively. Why? Because in coding, you need to you grow the tree recursively by recursion, right? Grow the tree iteratively or recursively until some long enough depth, okay? Using this, what was this? The local error. So this local error gives us which feature we should split and which threshold, right? At every region, in every region. Then prune the tree iteratively until its depth becomes the desired path, depth. So grow it and then prune it using the global error. Okay. We will see that for classification, it's very similar, but the difference is in the loss. Why? Because I think it's obvious to you. In regression, mean squared error is good because it's continuous label. But in classification, we don't use mean squared error. We use other errors and we'll see them. Okay. Is it always necessary to prune the tree? Yeah. What? Yes, exactly. Sometimes maybe you are in a good fit, even, for example, here. So the question is whether it's always good to prune or not. Maybe sometimes we don't need to prune. Maybe your training error goes down, but for your data, your validation error also always goes down. When does this happen? It never goes up, almost. When does it happen? When we don't have, when the validation data is very similar to the training data. When there is no domain shift in the validation error data and training data, then we don't need to prune because it will work perfectly for the training data. And as we don't have any domain shift, it will work perfectly for the validation or test data, right? But if we have domain shift, then we don't want to overfit or become perfect for the training data. We want to become almost perfect, almost good for the training data. So it also works even when we have some domain shift, some amount of domain shift in the validation data. Okay. Now, decision tree for classification. When it is classification, it's usually called decision tree. Maybe sometimes they call the tree for regression also decision tree. Doesn't matter. Tree, decision tree. Okay. The tree can be used for classification. It is called decision tree because it decides the class label of the data points in its regions. Okay. The cost of the decision tree should be a loss for misclassification now. So the cost in the regression tree was the amount of deviation from the labels, which can be mean squared error. But now we need to have a loss for misclassification. Assume there are C classes and L denotes the label of the Lth class. Okay. So we have C classes and L denotes the label of the Lth class. We define this PML. What is it? As what was NM? It was the number of points in the region RM, in the child RM. Okay. The sum is over the points in the child region RM. And what is this? This is the indicator function. It means that it is 1 if the label of xi, which is yi, equals L. Otherwise, it's 0. What does it mean? What does this summation mean? How many points of the Lth class do we have in the region Rm, right? It counts the number of points in region Rm which have the label L, right? And then it divides over all of the points in the region Rm. So it's basically a fraction. PML is basically a fraction. How many points of each class do we have in that region? So PM1 means how many points of class 1 do we have in Rm? PM2, how many points of class 2 do we have in Rm, etc. Right? And we can do it for different regions. Rm goes from 1 to cardinality of T. Then, so Nm, you can write it as this in the denominator. It's the summation of all of the points in region Rm. It counts them. Okay. Now, as I said, PML shows what fraction of points in the region Rm have class label L. In other words, how pure the region is for the class label L. So if PML is close to 1, it means that this region is almost all of the points in that region have class label L, right? So how pure it is. Okay, we had this, I'm repeating it. We can have various cost functions such as these. What do we have? Misclassification error, Gini index, cross entropy. Okay, so we define various errors. What is this? This is misclassification error. Why? The summation is over the children regions, and 1 minus PML. PML, as I said, shows how pure that region is for the class label L. So 1 minus PML, it means how impure, how bad it is, right? Therefore, summation over them, it means how bad that region is for the class label L. So it means that the misclassification error, right? Gini index is this. It sums, so it's a nested sum. The first sum is the summation over the children regions, and the next summation is over the class labels, right? And PM it times, so we will have PML and PMK, right? So as I see, yes, I think. Give me a second. I think I need to double check it, but I think this is 2 sums. One sum over L, one sum over K. So L from 1 to C, K from 1 to C, where K is not equal to L. Did you get it? Okay. What do I mean by this? By this sum. I mean, I sum over the class labels twice. Okay. Class 1 and 2, class 1 and 3, class 1 and 4, class 2 and 3, class 2 and 4, class 3 and 4. That's it. I don't consider every class with itself. That's basically means this. Okay. All of the pairs of the classes. And what does this mean? So as I said, L and K. So we are considering the pairs of the classes. So once we have PML and once we have PMK. So we multiply them by each other. Why? Do you know? Do you know that? What's the rationale behind that? It's because if PML is large, so because they are adversarial, if the region is pure for one of them, it's impure for the other one. So if PML goes close to 1, PMK goes close to 0. So no matter which one is pure, either PML or PMK, the multiplication becomes very close to 0 because one of them is close to 0. So it's good. So it's pure. However, if both of them are bad, they are both close to half, for example. So they are not close, neither of them is close to 0. Therefore, their multiplication is not close to 0. Therefore, it's a measure of badness. That's why Gini index is showing how much badness we have. Did you get it? Because when PML and PMK are neither of them is close to 0, then it means that it's bad. And we are doing it for every pairs of classes. Okay. Also, we can have cross entropy loss, and this is the definition of cross entropy. Okay. So what does cross entropy do? It's basically saying that I want PML, that if you consider PML to be a probability to be high, I want the region to be pure for the L class, and I'm summing over the classes. So I'm saying that I want the region to be at least pure for one of the classes. Okay, this is what cross entropy is saying. If we draw them, if we plot them, this is a famous plot in trees. It's like this. For binary classification, where C is 2, it's like this, PML. So close to half, they will be like this. This is the error. This is the cross entropy error. This is the Gini index error. And this is the misclassification error. Here in this plot, cross entropy is scaled to pass through the point half and half. This is the point half and half, right? Because cross entropy doesn't pass through that point, we are scaling that. But to see, we want to see the pattern. You see the pattern? And what does it mean? What does this plot mean? For all of these 3 loss functions, the error is maximized when PML is close to half. What does it mean? It's completely confused, right? As I said, PML, when it is close to 1, it means how pure that region is. Okay? So close to 1, here, close to 1, the error should be almost 0. But why is close to 0 also the error is close to 0? Because when PML is 0, almost 0, another PML, PMK, will be close to 1. They are adversarial. If one of them is close to 1, the other one is close to 0. Therefore, in both of these regions, the error is low. But when PML is half, it's confused for all of the classes. Here, 2 classes. As here we have 2 classes, it is half the confusion, right? Okay, noise injection to data in trees. One regularization technique in trees is noise injection to input training data. This is also a regularization technique in deep learning. Okay, in any machine learning method, this is a regularization technique. So at some level, we shouldn't completely confuse the data with noise. The variance of noise should be negligible with respect to the data. Okay, and then this prevents overfitting. Recall the lecture of overfitting. This is the error for the validation data where the data is not in the training set. This is the error for the training error when the data is in the training set. Okay, then if we do not add noise to data, this sigma is 0. Why? Because we don't have noise. If the variance of noise is 0, it means that we are not applying any noise, right? Then this, we get this for training data. Why? This goes away. This also goes away. These 2 terms, by the way, are not important. These are constants, okay? This is also goes away, doesn't matter. Error, the validation error becomes almost a training error. What does it mean? I'm justifying why noise injection to data is good. Because when sigma is 0, this complexity term, which is important for finding out overfitting, goes away. It means that the validation error becomes similar to training error, and we never find out when we are starting to overfit. But when we add some noise to data, then we will have this term. Then we can check the validation error, and we see that it goes up. Okay, this is the justification for why noise injection to input data is good at some level. So we can do it for tree and it works. Random forest now. Okay. Bagging. For random forest, you need to know about bagging. Bagging is short for bootstrap aggregating. It was first proposed in reference 1, 1996. Okay. I already said that in the deep learning course, but for this course, I need to say this also. So it is a meta algorithm which can be used with any model, such as classifier, regression, etc. Okay, what is the definition of bootstrapping? It's this. Suppose we have a sample xi, I goes from 1 to n, with size n, where f of x is an unknown distribution of sample. Okay, we would like to sample from this distribution, but we don't know f of x. Again, let me explain it. I have some data points with some distribution, probability density function, PDF, right? If I know the PDF, I can simply sample from the distribution easily using the cumulative distribution function. For more information, see my tutorial on sampling algorithms, okay? There I have explained how we can sample from CDF of distribution, okay? From inverse CDF of the distribution. Anyways, however, we don't have here the PDF. We only have some samples of the PDF. We want to sample further. We want to sample more. What can we do? We can approximate sampling from the distribution by randomly sampling from the available sample. You have the available sample, randomly sample from the available sample. This is called bootstrapping. And in bootstrapping, we use simple random sampling with replacement. Okay, so what does it mean? Put these available samples in a bag, for example, and put your hand and take some of them, watch them, see them, and put those back in the bag and shuffle it again and take it again. So it's sampling with replacement. And the drawn sample is named bootstrap sample. In bagging, we draw k bootstrap samples, each with some sample size. Okay, in bagging. Bagging is short for bootstrap aggregating. So here, then we train the model HJ using the jth bootstrap sample, where j goes from 1 to k. What does it mean? We have k models, and these models, either they are the same model or they are different models. But eventually they will be different. Why? If they are already different models, for example, one of them is random forest, one of them is deep learning, one of them is LDA, whatever, then they are essentially different. But if they are all the same, all of them are trees, for example, but they will be different because their data will be different. The data which they will be trained by, it will be different. Because every time I'm bootstrapping different data points, and I'm using them to train the models. Okay, so I have k models and I train them. Hence, we have k trained models rather than one model. Okay. Finally, we aggregate the results of estimations of the k models. It's kind of a democracy. Okay, rather than saying that I have one model to decide, let's have several models and let's have some kind of voting. Okay, so it's called aggregating. It's in statistics. This is also called model averaging. So as you see, you're averaging the models, the result. This is the estimation of the jth model for the input x, right? And if it is classification, we need to have a sign because it's either between minus and 1, some score. So I can use a sign. I can say whether the class label is -1 or 1. Okay. Now let EJ denote the error of the jth model in the estimation of the observation of an instance. Okay, so EJ denotes the error of the estimation of the jth model. And assume it is a Gaussian distribution with mean 0 and variance S, and assume they are IID, independent and identically distributed. Okay, then what do? We denote the covariance of the estimations of two trained models using two different bootstrap samples by C. So each of these models have some variance, each of them has some variance, but the models also, they have covariance with each other, right? Covariance of estimation. So EJ squared is, so as I said, I think this proof is not required. We can simply say the variance of the model is S. I already said that here. The variance of the jth model is S, okay? Sorry. The variance of the jth model is S, right? But their covariance, let's talk about their covariance. the covariance is defined as expectation of EJ EL minus expectation of EJ, expectation of EL. Expectation of EJ EL is C, and expectation of EJ and expectation of EL are both 0 because we assumed that the mean of the models, the noise errors of the models is 0. So it becomes C. The covariance of the two models is C, okay? So the variance is S, the covariance is C. Now, let's consider the variance of f hat of x. What is f hat of x? Is the aggregated result after voting or model averaging, okay? So, consider this, f hat of x. I have this. This 1 over k is a constant, is not random, but variance is quadratic. Therefore, for coming out, it needs to be squared. Recall preliminaries. So 1 over k squared, then I have variance of this, right? We already proved in the preliminaries of this course that the variance of summation is equal to summation of variances plus summation of covariances, right? So I have these two, and this 1 over k squared is multiplied to both terms, right? Now, each of these variances is S according to equation 18. Therefore, and I have k of them. So this is ks. Also here, each of these covariances is C. And how many do I have? This summation, these nested summations. It means that, so one summation is over the, like some kind of rows. So you have k of them. The second summation is some kind of, if you see it as a matrix in the columns. So you have k squared. However, you are not considering the covariance of every model with itself. Doesn't make any sense. So you are eliminating the diagonal. So it's k squared minus k terms. So if you factor out k, it will be k times k minus 1. So it's this, k times k minus 1, and each of them is c. If you simplify the terms, it becomes like this, okay? I have repeated what we obtained here, okay? Now, it has an interesting analysis. What does it say? It says that if, do you follow me? Do you follow me? If the two trained models consider two models, two of these models, okay? If the two models are very correlated, then what happens? C becomes almost S. The covariance of the two models becomes like the variance of one model, right? Because they're very similar to each other. Then I can replace this C by S. If you simplify this, it becomes S. Why? Because 1 over k plus k minus 1 over k times S, this is 1, right? However, if the two models are too different, uncorrelated, therefore their covariance is 0 according to the Pearson correlation coefficient. Then what happens? I can put 0 here. Okay? Then this term goes away, so I will have this. Now let's compare equations 21 and 22. What does it say? It says that if two models are very similar to each other, the variance of estimation of the aggregated thing, model averaging, becomes S. However, if they are very different from each other, it becomes 1 over k times S. So if there are two different models, it's better for me. Or if there are k different models, it's better for me. Because the variance of estimation will be divided by k. It will be lower. I want lower variance of estimation. Why? Do you remember? In overfitting, we have high variance. The more variance we have, the more overfitted. So it's saying that I want to be less overfitted. So I want the variance of estimation to be low. Therefore, this equation 22 is better than equation 21. Therefore, I want the models to be different from each other, right? I think it makes sense. If you already have similar models, all similar models, why do you need several models? Just use one of them. But if you have different models, then it's good. Also in democracy, they say that let's have opinion of various people. all people shouldn't think similarly to each other, right? Something like that. Okay. And also it shows that bagging never is destructive. It is never destructive. It either doesn't help at all or it helps reduce the variance of estimation. It never increases that. And it prevents overfitting. By the way, it's also called, bagging is also called ensemble learning or model averaging, right? Okay, one of the examples of using bagging in machine learning is random forest, proposed in 2002. Okay, in random forest, we train different models, here trees. So the models in random forest are the trees, right? Using different bootstrap samples. Okay, so we talked about in bagging, we have different bootstrap samples, right? So in random forest, by the way, why do they call this forest? Because forest contains trees, and in random forest, we are having the models as trees, right? So that's why they call it forest. And why is it random? I will tell you. Because it randomly selects the samples. Also, it randomly selects the features for the trees. And why does it? So randomly selected samples is because of having different bootstraps, right? As we talked about. But why does it randomly select the features? Exactly, because it wants the models to be uncorrelated or very different from each other. So the variance of estimation becomes lower. Otherwise, a random forest will be similar to one tree. If all of the trees are similar, why do you need several trees? Just use one tree, right? So it also samples from the features in addition to sampling from the data points. This is the idea of random forest. Okay. There are variations of decision tree, but they all have the same base we discussed. Okay. Some variations are these. I don't go into the details of these, but you can take a look at all of them. The base is the same. So C4.55. They have some weird names such as C2, C3, C4.55. It was proposed in 1993. CART proposed in 1984. For example, for more information on CART, you can see reference 10. For more information on decision trees, you can see references 11 and 12. By the way, for random forest, we have other various versions too. For example, extremely random forests or these things. There are various things, okay? But all of them have the base that we talked about. They are using bagging, okay? For more information on trees in machine learning, you can see the book of Hasty and Tibshirani, Elements of Statistical Learning in Springer. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo and Professor Hoda Mohammadzadeh at Sharif University of Technology. Okay. References, we go very fast. So bagging predictors about bagging. This one also explains the bagging. This one, I don't remember, but I think it was related to bagging. This one is about ensemble learning. So this one is about model averaging, Bayesian model averaging in the statistics. This one, model selection and model averaging, again about model averaging. This one is the paper of random forest, classification and regression of random forest. And as you see, it was proposed by people in the statistics, R news. People in statisticians use the R programming language. Program for machine learning. This is the paper, I think, for one of the decision trees which we talked about. This is, I think, C4.55. This one, classification and regression trees, CRC press. It is for the CART, as far as I remember, CART tree. This one also analyzes the CART decision tree. This is new, by the way, 2019. This is the Elements of a Statistical Learning book, and this is classification and regression trees, a review paper. Okay, let's go to the next topic. Any question? Logistic regression. So after this logistic regression, we already have covered most of the basic classification and regression algorithms. Then we'll cover other topics in machine learning, okay? So logistic regression. Logistic regression is popular in biostatistics and bioinformatics. And by the way, its name is misleading. It's not for regression, it's for classification. It's a classification algorithm. But why? Why do they call it logistic regression? Recall preliminaries. We said regression, you can see it as a special case of classification because you can predict the score of belonging to a class by regression and then use a threshold to say whether it belongs to class 1 or 2. So this is a technique used in logistic regression. Okay, so we predict the score of belonging to a class or probability. So let X be d-dimensional, be a data point, and Y be a scalar class label. The Bayes rule is this. This is Bayes rule. So this is posterior, likelihood, the priors, right? Now, in contrast to linear discriminant analysis, LDA, which we talked about, logistic regression works on the posterior directly rather than working on likelihood and prior. So consider this numerator in the Bayes rule. LDA works on the numerator, the likelihood times the prior. Recall how we proved the LDA, right? It's because if you remember, we equated the posteriors to each other and we ignored the denominators of the Bayes rule. So basically we were saying that let's equate the likelihood times prior equal to the likelihood times prior of the other class, right? However, logistic regression raises a philosophical question. Why should I work on the posterior, on the likelihood and the prior? Let me directly work on the posterior. Okay, this is what logistic regression says. And what is posterior? It means probability of Y given X. It means that given the data point, what is the probability that it belongs to a class Y or something like that? Which class? Okay, logistic regression is a binary classifier where it assigns the probability between 0 and 1 for belonging to one of the classes. So 1 minus that probability will be the probability of belonging to the other class. The logistic regression logistic function is used in logistic regression. Hence the name logistic regression. So logistic regression uses a function named logistic function. The logistic function was initially proposed in 1845. Very old. For what? For modeling the population growth. Why? Because as we see, this is logistic function. Okay. Why is it good for population growth? Because here, when we initially we don't have enough population is low, but people will mate and they will have children, so the population goes up. It goes up until some point where, because of lack of food and health and lack of food and conditions, then the population, some people die, then it stagnates, right? This is the reason it can be good for population growth, modeling population growth. Then it was further improved in 20th century. And in reference 3, you can see the history of logistic regression. Okay. What does it do? It considers the logistic regression. It considers classification problem as a regression problem where it regresses or predicts the probability of belonging to a class. It first considers a linear regression. So what does it say? Logistic regression says, okay, let me use regression for the sake of classification. Then what regression method do I use? Let me use linear regression. However, there is a problem with linear regression. It's unbounded. I want it to be the probability. I want it to be like a probability between 0 and 1. I want it to be a probability between 0 and 1. So its value should be bounded between 0 and 1. Therefore, for bounding it, I use logistic function, or also called sigmoid function. And what does it do? It maps the unbounded data value to between 0 and 1. So this is sigmoid or logistic function. And then rather than minus x, because rather than x, I can put anything. I can put any value. I can put Benjamin, 1 over 1 plus e to the minus Benjamin, right? Rather than x or Benjamin, I put beta transpose minus beta transpose x, right? So rather than x, I can put Benjamin, or I can put minus beta transpose x. So the formula becomes 1 over 1 plus e to the beta transpose x. That minus goes away. And then the function becomes like this. So this is the function used in logistic regression. This is the original sigmoid or logistic function. Okay. So I say probability of this probability given x. What is the probability that it belongs to the class 1? It's this. Therefore, the probability of belonging to the class 0 is 1 minus the other probability, which is this. Okay, plot it here. As you see, they have opposite behaviors, because when one of them goes to 0, the other one should go to 1. And beta here is a layer number parameters. You remember I said it's using some kind of linear regression beta transpose x plus beta 0, but it's unbounded, so it's using that inside the logistic function. Logistic regression can be seen as a neural network with only one neuron, where the activation function is a nonlinear sigmoid or logistic function. So it's one neuron in neural network. So you have x1 to xd. So you multiply it to the weights beta 1 to beta t, but you also consider beta 0 for the sake of bias or DC signal or intercept. But where x0 is 1, it's kind of linear regression up to this point, but you pass it through a logistic function. Okay. Consider n data points, xi, and their labels yi. The labels are discrete, right? These are the target labels. Okay. Assuming that they are independent and identically distributed, so they are IID, then what happens? The posterior over all data points is this. The probability of y given x, you can write it as a multiplication of this probability y, because they are IID, they are independent. And what does it say? It says if the point is in the class 1, so I use its probability for belonging to class 1. If the point is in class 0, I use the probability of belonging to class 0. And I here is the indicator function, right? Okay. As the labels are either 0 or 1, okay, the target labels are either 0 or 1. This equation 4 can be simplified or restated in this way. This is a good technique in machine learning. Consider that. It's used a lot. I think this technique was also used in word2vec. Do you know word2vec? This is an NLP algorithm. Okay, so it's used a lot in machine learning. If we have time, I will go over this in one of the 2 courses. Okay, if we have time. So we have this P of y equals 1 given x to the yi to the power of yi. So I'm bringing yi and 1 minus yi to the powers. Why? Let's analyze it. If yi is 1, I will have this term. This term goes away because everything to the power of 0 is 1 except 0. Okay. So everything to the power of 0 is 1. So if yi is 1, I will have this. If yi is 0, I will have the second term. Okay. And the other term becomes 1. And times 1 in multiplication doesn't have any impact. Okay. So now substituting equation 2 and 3 in this equation. What was equation 2 and 3? The logistic functions used in logistic regression. So if I replace these with what I had, I will end up with equation 6. Okay. Now the log posterior. So this is posterior. Equation 6 is posterior. Now I do the log posterior. Why? For two reasons. This multiplication is a pain in the neck. I want to make it summation. And we know that log of A times B is log of A plus log of B. Therefore, log of product is equal to summation of logs, right? That's just one reason. Another reason, I have exponential. They are also pains in the neck, okay? Therefore, in order to get rid of this exponential, I use their opposite operator, which is logarithm. What happened? Oh. Is that better? Okay. Are you fine? Okay, that's good. So I'm using the opposite operator, which is logarithm. I take log of this. So if I take log of this, then I have this multiplication. This log of multiplication becomes sums of logs. So sums of logs. And by the way, the technique that I told you, I have yi and 1 minus yi in the powers. This logarithm technique also brings the powers back behind the logarithms. So this also comes behind these two. So I will have them here. Okay. And by the way, I also use the fact that log of A over B equals log of A minus log of B for this. Okay. And then what do I do? This becomes simplified. Log of exponential, they cancel each other. So it becomes only the power here, beta transpose xi. Okay. And then what do? I multiply these to the terms. So I have minus this, and also minus times minus is plus yi times this. Right? Understood? And then what do? Interestingly, these two cancel each other. Interestingly. Therefore, I will have this. Right? Now, the log posterior, we simplified it and it became this. We need to maximize this. We need to maximize the posterior, right? The probability of belonging to the classes. We need to maximize it. Either posterior or log posterior. Here we are maximizing the log posterior. So for maximization, we need to do optimization. We can use gradient descent, Newton's method, first order, second order. Here we use second order optimization, Newton's method. So Newton's method can be used to find the optimum beta. So we need both first order derivative and second order derivative. So first derivative or gradient, let's take derivative with respect to beta. This is linear with respect to beta. Its derivative becomes yixi. This one, what is the formula for the derivative of logarithm? It's logarithm of a, its derivative becomes logarithm of a over a, right? Right? And also we need to do chain rule also, because inside of that we need to do chain rule in derivative. So it becomes, this derivative becomes this, right? And what happens then? So I'm just bringing this to the numerator as this, and I'm factoring out, factoring out xi. Xi is a vector. Okay. Now we calculate its transpose. So this was, let's transpose this to become this. So this is the vector part becomes transpose. Why do I transpose it? We will see. I need that it's transpose. Okay. The second derivative or Hessian is this. I can write it as the derivative of the first derivative. But the first derivative, I need to take transpose. Why? I need to take transpose because here I need to have beta transpose. I can't write it as beta transpose beta because beta transpose beta is a scalar. But beta transpose is a matrix. I know that the Hessian should be a matrix because the cost function was a scalar. The variable was a vector. I know that the derivative of a scalar with respect to a vector is a vector. And therefore, the second derivative will be a matrix because it will be the derivative of a vector with respect to another vector. It's a matrix, right? So I have this. This is a gradient I'm replacing here. So I need to take derivative of the transpose of the gradient. Then what happens? We know that derivative is a linear operator, so it passes through the sum. So it comes here, it passes through the sum. And then I have this. I define this term, which has appeared here, to be probability of xi given beta. This is my definition. Okay, this is notation of definition. Okay, now I put this definition inside, so I will end up with this. So this is the second derivative, but we still need to calculate what I defined, and we need to calculate it. So I'm now calculating that derivative of probability of xi given beta. So I need to take derivative of this term, right? Now I use the formula for the derivative of fraction. You know that, right? The denominator becomes a square. Derivative of, I think it was this, right? The derivative of numerator times derivative minus the numerator times derivative of denominator. So this is exactly what I have done. I have used the formula for derivative of fraction. And then I factor out xi. By the way, note that this is a scalar, so it can move back and forth in the multiplication. So I factor out xi. And then what happens? Interestingly, these two cancel each other, right? Therefore, it simplifies to this. Then what happens? I can write this term as a multiplication of these two terms, right? Interestingly, this is what I defined. This is probability of xi given beta, and this second one is 1 minus probability of xi given beta, right? Okay, now let's substitute this in equation 9 again. You remember? So we had this. We already calculated that in that slide. Now let's substitute it in equation 9. It gives us equation 10. Okay, so we calculated the Hessian also, where probability of xi given beta is what we defined in equation 8. Now it is possible to write the Newton's method in matrix form. So what do we do? Rather than doing it element-wise, let's do it in matrix form. So I put xi to xn, I have n data points, each of which is d-dimensional. I put them here. Each of them is a column vector, right? I also put 1 at the end for the sake of bias. Okay, so it becomes d plus 1 rows and n columns. I denote it by matrix X. Also, I define a diagonal matrix whose diagonal elements are D as the matrix W, and it will be n by n because I have n data points, right? Why am I doing this? What's the reason? Because in Hessian, I have this term. Therefore, I'm defining this W. Okay. And I put the labels next to each other as a column vector Y, n dimensional. Also, these terms, I have them in the gradient and Hessian. So I define it as the vector P, which is also n dimensional because I have n data points. Okay. Now, the gradient and Hessian, I can write them in matrix form. If you put these, consider these in the equations of the gradient and Hessian, which are equation 7 is gradient, and equation 10 is the Hessian, right? Just compare them with these formulas that we define. You will see that they become equation 11 and 12. I can write them in matrix form. Now, Newton's method. What is Newton's method for maximization? It says that the variable equals the previous variable plus. Here we have plus rather than minus. Why? Because we are maximizing it. Plus Hessian inverse times gradient, right? So plus Hessian inverse times gradient. And what is this is gradient. This is gradient. This is Hessian. What is its inverse? This is X, WX transpose inverse. But we have plus the Hessian inverse, and this minus is because of the minus inside the Hessian. It's not because of the minus in the formula of optimization. Okay? And tau here is the iteration index. It is repeated until the convergence of beta. I think it's obvious. Okay. Now in the test phase, what do? This was training. In the test phase, the class of a point X is determined as this, estimated as this. So we feed X to the formula of the logistic function that we had. If it is greater than half, so it's a number between 0 and 1. If it is greater than half, it's class 1. Otherwise, it's class 0. Why? Why is it class 1? Because this was a probability of y equals 1 given X. Right? If I had used here the probability of y given 0 given X, then I should put 0 here. I think it's obvious, right? Do you follow what I'm saying? Okay, now comparison to LDA. Logistic regression estimates d plus 1 parameters in beta, right? Do you remember? Beta is beta, the d plus 1 values. So we have d plus 1 optimization variables. However, LDA estimates many more parameters. Like what? So if you recall the LDA lecture, it estimates a prior for each class, which is each class is the prior of each class is one dimensional. It's a scalar. Therefore, we have two classes. 2 times 1 is 2 parameters. We also have mean of each class. Mean of each class is d-dimensional, and we have 2 classes, so 2d parameters. And covariance matrix of each class is d times d plus 1 over 2 parameters. Why? Because covariance matrix is diagonal, so we don't need the one of the triangles, half triangles of the matrix. Therefore, and we have 2 of them, so 2 times d plus 1 over 2 becomes d times d plus 1. If you sum all of these values, it becomes d squared plus 2d plus 2. Compare this and d plus 1. Of course, d plus 1 is much less than this because that has d squared. Therefore, it means that LDA has a lot more parameters to learn. Okay. So in this way, logistic regression wins. Also, LDA assumes the distribution of each class is Gaussian, which may not be true, right? However, logistic regression does not assume anything about the distribution of data. Did we make any assumption on the distribution of data in logistic regression? No. So it has less number of assumptions. And according to Occam's razor in logic and philosophy, what? The less assumptions we have, the simpler explanation is the better. Okay, better. So that was logistic regression. Some slides of this slide deck were inspired by teachings of Professor Ali Qudsi at the University of Waterloo. And this one. Okay, this one, I think this was the paper proposing logistic function for the population growth, 1845. It's not even in English. Okay. Estimation of the probability of an event as a function of several independent variables, 1967. I said it was improved in the previous century. Also, the origins of logistic regression, you can see it as for the history of logistic regression, this paper. Okay, let's have a break and come to 17 minutes to 9. Okay, only 15 minutes break. Okay, thank you very much. Let's have a break. So, just give me a second. Okay, now before we continue, so far we almost covered most of the basic algorithms in machine learning. Let's take a look at them very fast. So I'm just searching this scale learn something. Okay, scale learn and scalar is also pronounced as scikit-learn. So, for example, this page, it is classifier comparison. Search scalar classifier comparison, you will have it. So, for example, it is comparing what? This is input data, this is nearest neighbors, then SVM, then RBF SVM, then Gaussian process, then decision tree, then neural network, then decision tree. And one of them was decision tree, one of them was random forest. This one is ADA boost. We will cover boosting soon. Naive Bayes we already covered. QDA and LDA we covered them. So we covered most of the basic algorithms. This is for classification. And some examples. So the code for generating these figures. I think you know what these mean, right? Here, red and blue means that the different classes in the training data set, and here it's showing the score of belonging to the classes, the scores, right? Okay. So here, these are red and blue, and these are the scores in the space, the scores of belonging to the classes. So here, this is the page for linear discriminant analysis, the scikit-learn, and most of them have fit, transform, and transform, or some other thing. So fit, the method fit means that train. So it takes fit, as you see, fit. Do you see that? Let me zoom. Where is that? Fit. What does it say? It takes X and Y. These are training data set, data and labels. Fit trains. Okay. Fit transform does it. By the way, transform, it takes X. This is test data. The test data can be, you can pass the training data as a test data also, doesn't matter, right? So X is the data which is either training or test or validation, whatever. You pass it after training. So you need to first fit. After training, you use transform for the sake of testing phase, right? Fit transform trains and tests on the same data. So trains on the data and tests on the same data. And other things. So most of them have these three important methods. And that's why in the assignment, I said most of the codes for these classifiers are like each other, very similar. So the only difference is they're importing and how you make the object, and then you will have the for loops. You split the training and test and these. So most of them are like each other. And this is for linear discriminant analysis, which we covered. This is for QDA, quadratic discriminant analysis. There are two pages. One of them is this. The other one is actually a scalar.discriminant analysis quadratic discriminant analysis. So I'm not sure which one is the difference, but I think they are the same. For the assignment, use the link that I sent you. Okay. So this one, scalar SVC, this is for SVM, and kernel SVM both. Okay. So here, if you set kernel to be linear, as shown here in this line, what does it do? It reduces to linear SVM. Why? Because recall what we talked about. The kernel SVM uses kernel trick. When we are using kernel trick, linear kernel doesn't do anything. So linear kernel becomes like, it doesn't do anything. It's not kernelizing anymore. So it becomes linear SVM. However, scikit-learn suggests that as SVC is a bit slow, when you want to use linear SVM, don't use SVC with linear kernel. Instead, use linear SVC, this page. Okay, this is faster, much faster. Just give me a sec. Yes. Okay, this one, k-nearest neighbor classifier, KNN algorithm, we already talked about. This is, no. We also, I can't find it. So we also have KNN regressor. Okay, so we have KNN classifier in scikit-learn. We also have another page in scikit-learn, k-nearest neighbors regressor. So we can have for classification and regression both. And this one Gaussian naive Bayes. We already talked about it. We already talked about Gaussian naive Bayes for classification. This is decision tree classifier. We talked about it. This is decision tree regressor for regression. We talked about it. This is random forest regressor. We talked about it. This is random forest classifier. We talked about it. Right? All of them we talked about. This is logistic regression. We just talked about it. This is Gaussian mixture, which we will cover in this course later. Okay? Which is a mixture distribution. Now let's. What? No, that's okay. So okay. Now let's go to boosting. Guys, this one, please focus. This one needs patience. Okay? Its theory is long a bit. But if you are patient with theory, okay, it will bloom, okay, and you will enjoy it. Okay, you shouldn't get in this course, in these courses, the only prerequisite is patience with math. Okay, yeah. you shouldn't get tired or frustrated with math in the middle. Okay, boosting. Definition. Listen, guys, listen. Definition. Boosting is a meta algorithm which can be used with any model, classifier, regressor, regression, etc. So meta algorithm can be used with any algorithm, right? Okay. For binary classification, for example, if we use boosting with a classifier, even slightly better than flipping a coin, we will have a strong classifier. We'll see that. We'll see the reason mathematically. Okay. So what does it mean? The idea of boosting is this. Rather than having one strong classifier, regressor, whatever, let me have several weak classifiers or regressors, but a bit better than random. A bit better than random. So they are weak, but a bit better than random. Then we have them all together, they will become strong. So again, it's like collaboration in the real world. We are all weak, but together we become strong. Okay. So thus we can say boosting makes the estimation or classification very strong. And hence the name boosting. It boosts. Okay. In other words, boosting addresses the question whether a strong classifier can be obtained from a set of weak classifiers. Can we do that? And yes, we can. Okay. The idea of boosting, listen, guys. The idea of boosting is to learn K models in a hierarchy, okay, where every model gives more attention, larger weight to the instances misclassified or estimated very badly by the previous model. Again, I have several models, either regressor, classifier, whatever. First, I give the training the instances to the first model, H1. It classifies or regresses. On some data points, it works well. On some data points, it doesn't work well, right? For the points where it doesn't work well, I give more attention to in the next model, right? So the next model, every time, the next model should give more attention to the points which were estimated poorly by the previous model. So H2 attends or adjusts weights and gives more weight to the points which are poorly estimated by H1. Then, so we have a hierarchy, okay, until HK. So this is estimation of H1 for input X, estimation of H2 for input X until the end. And then we have a linear combination of them by some by some values, alpha 1 to alpha K. We sum them, it gives us F hat of X. So as you see, it's kind of a model averaging again. It's kind of a model average, similar to what we had in bagging, but in another way. Now we have a hierarchy. Okay. Finally, the overall estimation or classification is a weighted summation average of the K estimators, like this, right? For an instance X. If the model is classifier, then we need sign, right? To become either +1 or -1, which is the majority voting. You can see this as majority voting. What do I mean by majority vote? I say it's class 1, you say it's class 1, you say it's class -1, you say it's class -1. We say we kind of which is the majority vote. Okay. Definition again. Different methods have been proposed for boosting, various methods. Okay, so boosting is a family of algorithms. One of the most well-known ones is AdaBoost, also pronounced as AdaBoost. AdaBoost, doesn't matter. It's short for adaptive boosting. Proposed in 1996. The algorithm of AdaBoost for binary classification is shown below. So the AdaBoost algorithm is this. What does it say? Initialize all of the weights to 1/n. N is the number of points. Okay. So all of the weights, all of the points will have equal weights, 1/n, where the summation of weights will be 1. Uniform weights. Now for J from 1 to K, what is K? The number of models. So I'm having a for loop over the models. Okay. What do? I have some LJ loss. Okay. LJ loss. We will talk about it. Then I say which one I take argument of LJ to find the model HJ. In other words, HJ solves this optimization problem. It minimizes some loss function LJ. Okay. Then I define some alpha J. We will prove all of this. Alpha J, which is log of 1 minus LJ over LJ. What is alpha J? Some weights here used in here. Do you remember what was WI? This is the weights of the points. I said, if a point is poorly estimated by the previous model, I need to weight them, right? Initially, the weights were uniform. But now in line 5, I update the weights in this way. The previous WI times exponential alpha J and this indicator function. What does this indicator function say? Exactly. It says that whether yi, the label of the point, whether the estimation is not equal to the target label. In other words, if my model J has estimated wrongly, mistakenly, this indicator function becomes 1. If it estimates correctly, then this indicator function will be 0. Right? Yi is a target label, HJXI is the estimated label. Okay. Now in this algorithm, LJ is the cost function minimized in the jth model HJ, and I is the indicator function. Okay. Wi is the weight associated to the ith instance for the weighting it as the input to the next layer of boosting. As I said, these are the weights. Okay. Note that the cost in AdaBoost. Now I'm defining LJ used in line 3 of the algorithm. LJ equals this. What is it? Summation of I from 1 to n. Wi indicator function yi not equal to hjxi over summation of wi. What does it say? So basically, this indicator function says is 1 when I estimate incorrectly. Okay, the model estimates incorrectly. So it's basically saying that how many incorrect estimations do I have? Okay, how many, assuming this is classifier, okay, this indicator function says whether my HJ, the jth model, is estimating the class label mistakenly, then I'm counting them. This is a numerator, but with some weight, right? If I if I classify all of the points correctly, estimate them correctly, this LJ becomes 0, all of them, right? The more misclassification I have, the bigger the LJ becomes. Okay, therefore, it's a good loss function. I want to minimize that because I want it to become 0. It means that if it becomes 0, it means that I have classified all of the points by the model J correctly. Okay. Here we can have several cases which help us understand the interpretation of the AdaBoost algorithm. Now consider the cases. Are you following me? Now consider the cases. If an instance is correctly classified, this indicator function is 0, right? And thus WI will be still WI without any change. Why? Take a look at line 5. I'm talking about this line. Case 1. My Jth model estimated the class label of xi correctly. Okay. Therefore, inside the indicator function is not true. Therefore, indicator function is 0. Exponential of 0 becomes 1. E to the 0 power 0 becomes 1. So Wi equals Wi, the previous Wi. It means that if my model Hj estimated the class label of xi correctly, don't change its weight for the next label in the boosting. Okay, of course it's correct. It makes sense. If an instance is misclassified, then this indicator function becomes 1. Therefore, this becomes Wi equals Wi e to the alpha j. Right? Now, 2 subcases. So for the misclassification, we actually update Wi. Now 2 subcases. If the classifier, 2 subcases. If the classifier which classified that instance was a bad classifier. Again, consider in this case, which divided into two subcases, my classifier misclassified the point. Okay, misclassified the point. Now I'm discussing whether I should trust this classifier which misclassified or not. As you see, in this case, I'm updating Wi. However, there is alpha j. We can have 2 subcases over alpha j now. Okay, alpha j. So if the classifier which classified that instance was a bad classifier, its cost would be like flipping a coin, right? It's random classifier. Then LJ becomes almost half, right? Assume LJ is the probability of belonging to the class. If it's half, it means it's binary classification. It's completely confused, right? Therefore, now take a look at line 4, alpha j. It means that if you set LJ to half, what happens? Alpha j becomes log of half over half. This is 1. Log of 1 is 0. Log of 1 is 0. Do you agree? What does it mean? Alpha j here becomes 0. Again, e to the 0 is 1. It means that Wi is not updated. Okay, interesting. So, although it was misclassified, but as it was a bad classifier, I don't decide based on that. I don't change the weight. What? LJ is the cost, is the probability of belonging to the class. LJ is defined this here. It should be close to 0. Okay, it should be close to 0. But when it is half, what does it mean? It's completely random. It's flipping a coin. Okay. So then it means that if it is not good classifier, I should not make any decision based on that. Do you make your decisions of your life based on some stupid idea? No. If you know that the idea is stupid, you just don't make any decision based on that. right? You ignore that. That's exactly what boosting is doing. However, if the idea is clever, important, you make decision based on that. If the classifier which classified that instance was a good classifier but misclassified, oh, this is a danger. It was a good classifier, but it misclassified. Therefore, I need to update my weight. I need to give more weight to that point. So this indicator function is 1 because of misclassification. Lj is not half. Therefore, alpha j, I think it will be greater than 0. Or it will not, at least alpha j is not 0. Okay. Therefore, we'll have this, right? And it means that we are updating wi. And this is also intuitive because the previous model in the boosting was a good classifier and we can trust it. And that good classifier could not classify that instance correctly. Therefore, we should notice that instance more in the next model in the hierarchy. I think alpha j will be greater than 0. Therefore, e to the alpha j is greater than 1. Therefore, wi is enlarged. So wi, whatever it was, becomes greater. More weight. Did you get it? So in summary, we covered these cases. If it is classified correctly, don't change the weight. If it is classified incorrectly, see the classifier. If it is a bad classifier, don't change the weight. If it is a good classifier, change the weight and enlarge it. Okay, make it bigger. Now, proofs of the formulas that we saw in the boosting. Theory based on additive models. Additive models can be used to explain why boosting works. In an additive model, additive model is a concept in statistics, okay? In an additive model, we map the data x to phi jx, where phi j is some mapping, some kind of mapping, for all j from 1 to k. What does it mean? We have several maps. We have k maps, okay? And then add them using weights beta j's. So we have a linear combination of the maps. This is exactly additive model, right? We saw an example of it where radial basis function network, if you have the deep learning course, we have seen that. This is related to deep learning course, RBF network. It's not in this course, okay? But the RBF network is an example of additive model. Another example of additive model is boosting. Is boosting, which we are covering in this course, okay? So now consider a cost function for an instance. Consider this cost function. L, y, h of x. Y is the target label, h of x is the estimated label. And this y is the observation or label for x, and h of x is the model's estimation of y. This cost is intuitive. Why? Because when the instance is misclassified, what happens? Y, the signs of y and h of x will be different. For example, one of them is +1, one of them is -1, right? Therefore, this becomes less than 0. When this is less than 0, this minus y h of x is greater than 0. E to the positive number is a large number. However, when it is correct classification, y and h of x have the same sign, both are +1 or both are -1. So y h of x is greater than 0, minus f of y h of x is less than 0, e to the negative number is low. Therefore, this makes sense to be a cost. For misclassification, it is large. For correct classification, it is low. Okay. Now, if we add up the cost over n training the instances, we have n of them. So we have summation over this cost. And now we have yi and xi because we have several points, right? And L I denoted by LT, which is the total cost. Okay. In equation 4, phi of x is summation of beta j phi of jx j from 1 to k. This was additive model. Here you had this, right? Equation. Okay. If we rename the mapping to h of x, so I assume phi j of x is h of x. Okay. And what is h of x in boosting? The model, the jth model, the output of jth model. So this basically means the output of the jth model for the input x. And this is the total aggregated result. Okay. As you see, boosting can be seen as an additive model. Okay. Now we can write this expression as a forward stage-wise additive model. What does it mean? We'll see. In which we work the models one by one, where we add up the previously worked models. I think these two equations completely explain what I mean. So you consider fq minus 1 to be summation of beta j hjx j from 1 to q minus 1, and then you put this here plus the next one, beta q hq x. So start from q1 or 0, 1. Then what happens? f0 becomes only beta 0 hj0 x. Then q equals 2 becomes f1 becomes f0 plus beta 1 h1. So every time I add the next element to the summation. I think it's obvious, right? In other words, what I mean is this. I have several candies. I take the first candy. Then for the next candy, I take another candy. I put it in my bag. For the next candy, I take the bag, the 2 candies. I take the third candy. I put it in the bag. Every time I'm adding one by one, right? And h of x, which is the last one, which is all of the summation, is the last fk of x, the last one, right? Because in the last, all of them have been aggregated, have been summed, as shown in equation 7. Okay, therefore, minimizing the cost, equation 6, what was cost? This one, which we talked about, equation 6. This, I have repeated it here, for the jth model in an additive manner is this. Now I'm writing the cost in an additive manner, forward stable additive model. How? In this way. So I'm, rather than h of xi, I'm putting this. Where did I get this? From this additive forward stage-wise additive model. H of xi, I have put it fj minus 1 xi plus beta j hj xi. Note that I'm only in this cost, I'm only considering the jth model. Here, I don't have hj, I have h. I'm considering one model. But when I am considering, I have several models, I'm optimizing them separately. So as you see, my optimization variable is beta j hj. Okay. So for the jth model, this h of hxi becomes fj minus 1 xi plus beta j hj xi because of the forward stage-wise additive model. Okay. Now I multiply these to the terms. So I will have this. I have this. Also, I have used the fact that e to the ab, e to the a plus b equals e to the a and e to the b. I'm using this property also. Right? That's why I have 2 exponentials here. Right? Now, what happens? I'm repeating it here. We found this. Optimization variables are beta j hj. The first term, this is the first term, is a constant with respect to beta j, right? And hj. So my optimization variables are beta j and hj, and this first term is a constant. So we name it by wi. I define the first term, which is constant, to be wi. Therefore, this equation becomes this, wi here, right? Now, as in binary add a boost, binary classification, we have yi and hj are plus minus 1, either plus 1 or minus 1, okay, the target and the estimated labels. Then we can say that I can rewrite this as this. How? What am I doing? I'm saying that, by the way, this wi is here, wi is here, and what am I doing? If yi and h of j xi are both having the same sign, are both plus 1 or both minus 1, meaning this indicator function, then their multiplication is 1. Therefore, inside the exponential, I have minus beta j, e to the minus beta j. If they are with a different sign, yi h j xi becomes minus 1, and with this minus also, they become plus 1. So I will have e to the beta j. But why did e to the beta j and e to the minus beta j why did they become behind the summations? Because they don't depend on I. I'm factoring them out of the summation, right? Okay, so however, wi is dependent on I. Therefore, they are inside the summation. Okay, what happens then? Then, do you agree that I can write this for this term, which appeared here? I can write it in this way. I can write it as summation of all of wi's minus summation of wi's if the estimation is incorrect. So summation of wi's for correct estimations equals summation of all of the wi's minus summation of wi's for incorrect estimations. If I replace this term with this, what happens? I will get these two terms. This is this term, e to the minus beta j, is multiplied to each of these terms. I will have these, and the rest, this is here. This appears here, right? So I'm repeating this, what we found here. Bear with me, and it will bloom. It will bloom. We had this. We found it. Then what happens? For the sake of minimization, we take the derivative and set it to 0. First order optimality condition. Take derivative, set it to 0. So, taking derivative of this with respect to beta j, what happens? What is the derivative of this with respect to beta j? Minus this, right? So this is a constant, appears here. This e to the everything, its derivative is everything, but we have minus beta j, so we'll have minus behind, right? And then what is the derivative of this with respect to beta j? This is a constant. We repeat it here. And again, it has minus, cancels with this minus, becomes plus, right? And then the third term, again, its derivative with respect to beta j, it becomes itself. Set it to 0. And it is a scalar because beta j is a scalar. So what happens? Give me a second. What were we doing here? Okay. Yes. I think I rearrange it to become this. Am I right? Yes. I think I'm rearranging to become this. Do you agree? Why? Because of this. Just this multiplied by this, the denominator multiplied the other side, is exactly what we have here. Right? And these two terms, I'm just are these two terms. I'm just factoring out summation of wi, indicator function of yi, not equal to hj xj, right? So I'm just rearranging these to become this. If you multiply these two terms equal to each other, these, and rearrange the terms, you will get this. Okay. Now, what do we do? According to equation 3, this was equation 3. Equation 3 said that, do you remember one of the initial formulas in this slide deck? That was the loss function Lj. This is exactly the loss function Lj. So I can replace it with Lj. Okay. And then I rearrange these. Lj will be this over this. I rearrange the term, so it became this. Now, what happens? Now what happens? If we, yeah, exactly. If we rearrange this term, to have only beta j, but write it in terms of Lj, if you rearrange it, you will get this expression. What?
And this was the formula for alpha j.
Exactly. We are deriving the formulas in boosting. So take logarithm from the sides, it will give you this. And this was alpha j. Recall the algorithm. It was which line of the algorithm? It was line 4 of the algorithm, alpha j. So alpha j equals 2 beta j. Okay. Now let's continue. According to equations 8, 9, and 10, I have repeated them all here. This is equation 8, 9, and 10, which we had. Okay. So these two were the forward stage was forward thing, and this is wi. Okay. Now I can replace fj minus 1 xi by beta j hj xi according to this. Okay. For the jth model, for the jth model. Do you know why? But give me a second. That's a good question. Fj minus 1 xi beta j hj it's a good question. I need to think about it. If I find any answer, I will answer it in the next session. Yes. Do you know, I think the reason that we don't have summation is that we are considering only the jth model. Do you remember? Even when we started from, where did we start from? Here. I don't have summation here because I'm only considering the last equation here. This. I don't have summation here. I'm using this. Okay. I'm using this. I'm only optimizing for the jth model.
But we are using that because H has the summation. HG has.
Yes. No, H, yes, exactly. H has the summation. No. FQ minus 1. FJ minus 1 has a summation inside. Right? So this makes sense, but
if we do FJ, the summation should also. Because we are also taking into consideration the previous model, right?
Yeah. Yes, I need to think about it.
So,
a big question mark. Yes. So the question for this to be recorded is that why don't we have summation here according to what we have here? Why there is no summation here? I need to think about it. That's a good question. Thank you. But if any of you find out, or if you on YouTube, when you're watching it, find out, either you tell me or you write it in comment. Okay. I want to know the answer. But thank you. So, but accepting this, if we accept this, okay, then what happens? As we have yj at jxi plus minus 1. Why? Because yi and hj, the target label and the estimated label are either plus 1 or minus 1. So their multiplication is either plus 1 or minus 1. Then what happens? We can write minus yi at jxi as two indicator function of not being misclassification minus 1. Why? Let's see. If yi is correct, if we have a correct classification, this indicator function becomes 0, and this becomes minus 1. And that's correct, because these two becomes 1. Minus 1 times 1 is minus 1. That's correct. If yi is not equal to hjxi, we have misclassification. Then the right hand side is 2 times 1 minus 1 is 1, and the left hand side is also 1, because this is minus 1, and times minus 1 becomes 1. So this is correct for two cases. Okay. Now what am I doing? I'm replacing what I have here as yi at j by this equation, right? By this equation. However, so this becomes, I need to write it down so for you to understand what I'm talking about. So minus minus yi at j of xi, I replace it with 2i indicator function of yi not equal to hj xi minus 1. Okay. However, I know 2 beta j is also alpha j. Therefore, I replace 2 beta j with alpha j. Did you get it? Did you get what I did? And this is the rest. And note that I also have minus 1 here times beta j. So I will have e to the minus beta j. Everything clear? Simply replace in this inside the exponential. Simply replace minus yi at jxi with equation 13. And also note that alpha j equals 2 beta j. You will end up with equation 14. Okay. I'm also using the fact that e to the a plus b equals e to the a, e to the b. Okay. I'm also using this formula. Okay. And what is this? This equation, interestingly, we just proved that the formula of wi in the algorithm. Let's go back and see. Let's go back and see. Take a look at line 5. Memorize it for a while. Yes, exactly. The last term, there is an additional term which is multiplied at the end. This term. We have it. However, this factor does not have any impact on whether the instance is correctly classified or not. Is it? Does it? No. It's just a scale factor. Addition. You can drop it. Right? Now, beta. Let's go back. I also don't memorize that. What was that? Oh, it was in the additive model. The weights of the additive model. Or
So these are like,
let me complete my answer. So let's go back to where we started. We said boosting is summation of alpha j at j, but in additive model we called it beta j, and we found out that the relation of alpha j and beta j was 2 beta j. So it doesn't matter. So it's the weights in the additive model for the boosting. Okay, for combining all of the hierarchy. So here here, as I said, where was that? Somewhere here. Give me a second. Where was that? Oh, here. Here in equation 11, we found out that alpha j equals 2 beta j. So alpha j, beta j, both of them are the weights of the linear combination of the in the hierarchy in the boosting, in the additive model. So we proved the formulas of the boosting, other boost. Now upper bound on the generalization error of the boosting. So what do I mean? Generalization error, we want it to be minimized. Generalization error means the error on the test or validation data. I want it to be small. There is an upper bound on that. Theoretically, people have found out, proved that it can't go higher than some bound. So it is a small. It is good. It shows why boosting is working. Interestingly, initially, someone proposed boosting and it worked well. And then people were searching for the theory why it is working well. This is the theory for explaining why it is working well in practice. Okay. So upper bound is this. There is. Yeah. So it means that we will see. We will find the probability of error on the test or validation data. It is less than or equal to some value. And what do I mean by less than or equal? So if assume it's the plot of the generalization error, it can't go further than some bound. So this probability of error, we will prove it is less than some constant value. So it's a small. Right? We will see that. What? No, we are not making assumption. We are going to prove it. I told you ahead of time that we will prove that the probability of generalization error will be less than a value. So there is an upper bound on the generalization error of the boosting, and we are going to prove it. In binary boosting, we have +1 and -1 for yi, right? Also for the sign of f hat of xi. What is f hat of xi? The aggregation of all of the hierarchy in boosting is important. The sign of this is also important, right? In classification, you remember we take the sign. Okay. Therefore, yi f hat of xi less than 0 means that we have error for estimating the ith instance. In other words, if, for example, in classification, if target label is 1 and we say estimate it as -1, or if it is -1, we estimate it as 1. Their multiplication is less than 0. So it's an error. Okay. Therefore, for an error, we have this. Yi for the ith point. F hat of xi is the error. And if you want it to be an upper bound, so it should be less than or equal to some theta. We will prove what theta is. Okay. For some theta greater than 0. Of course, it's not a perfect world. We can't have a perfect classification. If theta is 0, it means that it's 100% accuracy. Okay. So recall equation 1. This was equation 1. We can normalize this equation because the sign of it is important. The sign of f hat of x is important, not its value, the sign. Therefore, I can simply normalize it. Okay. Now, according to equations 15 and 16, these two, we have what? So consider equation 15. I start with equation 15, and then I replace this f hat of xi with equation 16. So this denominator, I have a denominator. I multiply the sides by the denominator of equation 16, so it becomes here. It becomes here in the right-hand side, okay? And then I rearrange the terms, so I bring this to the other side, so I will have this greater than or equal to 0. Then I take exponential operator from the sides, e to the power these. So e to the power 0 becomes 1. Right? Let's continue. We found this. I'm repeating it here. Therefore, in terms of probability, so this is error, right? So this is probability of error. What is this? I can replace this with this. We've just proved that. So this is the probability of error. Probability of this becoming greater than or equal to 1. Now, there is an important inequality in probability theory. It's called Markov's inequality. Okay, this is the formula for Markov's inequality. For some a greater than 0 and a random variable x, so a is not random, x is random variable. Probability of x greater than or equal to some value a is less than or equal to expectation of x over a. This is a formula in probability theory, okay, called Markov's inequality. According to this, and equation 17, what happens? We take a equals 1 in Markov's inequality. So it will be probability of x greater than or equal to 1, less than or equal to expectation of x, right? If you set a to 1. Then what happens? You tell me. Interestingly, this is the right-hand side of equation 17. If we set this to be x, right? Now let's see, interestingly. I start with this, equation 17, left-hand side of equation 17. According to equation 17, this is equal to this. According to Markov's inequality with a equal to 1, it's less than or equal to this expectation. Okay. Now, we continue what we found. So we already talked about these two lines. Let's continue. So what happens? We know that expectation is with respect to data, okay, xi and yi. Therefore, this term is not dependent on data. So I can bring it out of expectation. I'm also using the formula of e to the a plus b equals e to the a times e to the b. Okay, and then what happens? B is according to the definition of expectation. I replace this expectation with its definition. So definition of expectation is this times 1 over n. Do you remember? Recall preliminaries. This is definition of expectation. So now we wait here. We go with another path, and these two paths would reach each other. Just as I said, we need to be patient in math here. Recall the formula of Wi in the algorithm. Wi, j plus 1 equals Wi of j e to the this. This was the formula in the algorithm, where j denotes the iteration index, okay? This can be restated in this way. So I can write this to be this. Why? Because yi and hj are either plus 1 or minus 1. Okay. Now what happens? It is not harmful to ADA boost if we use the normalized weights. That doesn't change the rationale of the ADA boost. So I normalize the weights. In the denominator, I have zj, where I define zj to be equation 21. Basically, it's summation of the numerator, but over all of the points. The numerator is only for the ith point. We had this, I'm repeating it here. Then what happens? Considering that, do you remember this? Initially, all of the weights were equal 1 over n. Okay, we can have recursive expression for the weights, recursively. So I have this, where k here, I replace j with k, doesn't matter. K is the iteration index. Then I can recursively write it in this way. So starting from wi1, I will have multiplication of the denominators, also the multiplication of numerators, right? Because here we have Wi. If we continue the recursion until all W1, the first iteration, W1 will be here. And for all of the W's, I have the multiplication of these terms. Okay. Now I can write this multiplication of new denominators as this. I replace W1 as 1 over n because of this. I also write this multiplication as this. Now what happens? Interestingly, product of expectations equals expectation of summation. In other words, e to the a, e to the b equals e to the a plus b. Therefore, I can bring this product inside expectation to become summation. And I know yi is not dependent on j, so I can bring it out of the summation. Because summation is over j. Then what happens? So now we consider this. The left-hand side, wik plus 1 equals this. Rearrange the terms. So what do I mean? I have this in the denominators times wi becomes this. The rest of the terms is this. I'm just rearranging this. This left-hand side equals this. I'm rearranging them to obtain equation 22. We found this. I'm repeating it here. Now we continue equation 19. What was equation 19? I don't remember. It was this. Do you remember? So equation 19, we said this probability of error, this was the probability of error, is less than or equal to this side, this right-hand side. I have repeated equation 19 here. Okay. But according to equation 22, which I have repeated above, what am I doing? Inside equation 19, interestingly, I have this term. I have this, sorry. I have 1 over n times this sum, this, am I right? Yes, exactly. I have this. So I can, this term is here. Therefore, I can replace this with what I have here. Agreed? I'm repeating what we found in the last slide here. I know it's a bit lengthy, but it will bloom. According to equation 20 and 21, I'm repeating equation 20. This is equation 20. This is 21. We found them already. We have this. So wi j plus 1 was this, and j1 zj in the denominator was this. So I'm replacing zj with what I had, with its expression. This summation also comes because of this because of this summation. Okay. Interestingly, this becomes 1 because the numerator and denominator are equal to each other. And interestingly, I know these are all interesting. That's why I say interestingly. This we just proved is 1. So we only end up with this. Therefore, we just simplified the probability of error. And what is this? An upper bound on the probability of error. This upper bound explains that the probability of error can't go further than some number. And if we continue the theory, we can prove that this upper bound is not huge, it's small. So the probability of error is small. That's why boosting works very well. In machine learning papers, when you are, or this many papers which work with probability, in probabilistic machine learning papers, all of them prove like this. They try to find some upper bound. And they use the formulas of Markov's inequality and these things a lot. So you are learning the techniques. We will continue this in the next session, but we covered very good part of the boosting. Maybe at the start of next session, we will restart from the probability of error again, because it's in the middle of probability of error, and we'll continue. Okay, thank you. Yeah. Just give me a slides back. Yes, just give me a sec.